Hey guys, how's it going? If you've been subscribed to the channel for a while, you may have wondered where the videos have been. Um, you know, I hate recording videos, and I hate editing them, splicing them, sticking them all together. It's very frustrating, it's very time consuming, and I actually bought a Mac Mini because I'd heard that that Mac was better for video editing, and the irony is that the last video I tried to record wouldn't actually render. And anyway, I gave up with that, switched back to my Windows PC, and I'm just gonna try to record things and just publish them as is. I did buy a little bit of software to make it a little easier. But anyway, so going on from previous videos, I had some videos about the X-Bank, and the X-Bank is something that I really want to work on, and I actually have been working on it. I've built a few prototypes, but I haven't been recording it. And so the goal here is to record rebuilding the thing and on the same hand explaining how it works. And so we're just going to get straight to it. All right, so the X-Bank, which I'm going to actually rename. So it was the X-Bank, but now it is no longer the X-Bank. I'm going to call it an overflow cell because it sounds less weird and possibly makes more sense. All right, so in an overflow cell, we have two components. One that is actually inside the overflow cell, and the other is a component we're connecting to. On this side we have the 12-volt battery, probably a lead acid, and on this side we have the lithium ion cell, and the idea here is that when the lead acid battery is almost full, it's gotten up to say 13.8 volts or more, we've really done the bulk charge, and we're running out of energy storage. Usually around that voltage, your solar kind of slows down because the battery won't take as many amps. So what we'll start to do at that voltage is trim the excess power and push it over to the lithium ion cell. Now, if this lead acid battery then drops below, say, 12.7 volts, we'll start to pump the power back up. The idea here is that this doesn't need anything too complicated with regards to a battery management system, because it's just one cell, 3.7 volts. We don't have multiple sets of cells to check. And it will only rely on a buck converter to bring power from 12 volts down to 3.7 volts, and a boost converter to bring power from 3.7 volts back up to the 12 volts. And that's pretty much it. I mean, it's pretty simple. The challenge, I think, will be efficiency. In any case, let's draw some more pieces here. Excuse me for looking to my side, but that's where I can actually see my camera to make sure that you can actually see what I'm drawing. So between between the two, excuse my cold, between the two we have a common negative, so we're just gonna connect that straight up, and up here, right here, is going to be the power circuitry. This is the circuitry that does all of the heavy switching, where all of the amps are going. This is not the control circuitry. We're going to need a brain to make the power circuitry work. So this is going to be the switches. We need a buck converter and a boost converter. We need to buck in this direction, and we need to boost in this direction. So we know we're going to have an inductor. All right. Okay. So let's start with the boost converter. Or not. Alright, well I messed that up, but whatever. We'll just put in the bits I know we're gonna need. So the buck converter will need a diode that allows voltage to flow in, or current to flow in this direction. And so, as you can see, because the negative is on this side, there won't be any current flow from the negative to the positive. We'll explain that in a minute. And then the boost converter is going to need a diode that allows current to flow in this direction. And given that this is 3.7 volts on this side and 12 volts on this side, when we connect the batteries to this circuit, or the battery and cell to the circuit, there shouldn't be any current flow initially. Now, the key to this is to have a switch. Actually, two switches. And there we go, we have two switches. This one is boost, and this one is buck. So what's going to happen? Wish I could get rid of this cold. Okay, if we want, well, let's go through this as a story. So your solar is collecting power, we're charging our lead acid battery, but the batteries are full. So there's excess power available, it has nowhere to go. These batteries pretty much kind of siphon off, and at that point there's energy you could be collecting that you're not. So when this battery is at 14 volts, we start to use the power circuitry to bring power down to and charge the 3.7 volt battery. And that's when we start to switch this switch. We start pulsing this and monitoring the current that's going through. When this is on, we charge the inductor and it allows power to flow. This is really regulating the current that's going through the circuit. When this is off, because power is going this way and we're charging, this diode allows the higher voltage to go through. Otherwise, we'd be causing some damage. Now, suppose then that the nighttime comes and your solar dies off, and you start to use your battery to run all of your appliances or whatever you're doing. You're using the battery, and there is no solar energy coming in. And so at this point, the voltage on your lead acid battery is going to start to dip. And that's when we really don't want to cycle the lead acid battery. We'd like to keep it at a minimum voltage. Let's say that the minimum voltage is 12.7 volts. So once this battery dips below 12.7 volts, we're going to start to use the boost converter to bring power from the 3.7 volt lithium ion cell to charge up the lead acid battery. And we just want to maintain that 12.7 volt the 12.7 volt voltage, so that there's really no current going in or out of this battery. And so at that point, we will start pulsing this switch. And so when we turn this switch on, the inductor is going to charge, and when we turn it off, there'll be a voltage, an increasing voltage here that should be higher than the 12 volt battery, and then this diode will allow the current through to charge the 12 volt lead acid battery. And that's pretty much it. nothing too complicated. And the challenge, I think, is efficiency. Trying to make this circuit efficient enough, because there are volt drops across these diodes, and depending on how much power you're trying to push to the lead acid battery from the lithium ion cell, that's going to be quite a bit of current. If you want to push 37 watts at 3.7 volts, you're talking about 10 amps, and 10 amps is no joke. And so there's going to be challenges there, but the goal right now is to build a working prototype, and so that's what we're going to do. Now on the other side of that, I want to try to keep this video short. We're going to have to have control circuitry, and that's fine. And so there's going to be a few different things here. There's definitely going to be capacitors. Excuse my really weird diagrams here. Hopefully you guys can follow it. Anyway, there's capacitors, and we're going to want to have an amp meter on each side. And we're also going to want to have a voltmeter, because we need to know what the voltages are, right? And that can just be a simple voltage divider. And then for the control circuitry, we will use an Arduino to control it. So the Arduino is going to want to have inputs from lots of different things. So we're going to want to know how many amps and what voltage is going through the lithium-ion cell. And then we're going to want to know the same thing about the 12-volt lead-acid battery. We're monitoring the 12-volt lead-acid battery to know what we're actually going to do. It's the voltage of the lead-acid battery that tells us whether or not we want to activate the boost circuit or the buck circuit. If we're sitting, if we're just sitting at 13 volts, we're probably not going to be boosting or bucking. So we're obviously going to want to have some PWM signals for the boost and the buck. And I think that these can just be single MOSFETs, as the body diode will work as a diode. Probably not ideal, but it'll do. Another thing we're probably going to want is a temperature sensor. And also something that can turn on a fan, because I would expect it's going to waste some power. On that note, this probably explains what we're trying to do. So on the note of wasted power, lead-acid batteries are not super efficient at charging, and they're really not efficient at charging when they're almost charged. Some people have made the argument that, an overflow cell, it's not going to be very efficient. It's probably going to be somewhere around 80% efficient, is my guess. Maybe 75, maybe 85. I don't know. But the point is that it's taking energy that would otherwise be wasted. And so, 75% of a kilowatt hour, or nothing of nothing. You get the energy or you don't get the energy. If you don't have somewhere to store it, then it's no good. And you can buy a bunch of lead-acid batteries, but you don't want to cycle them down, right? And you can buy lithium-ion batteries, but they're more expensive. And so, there's trade-offs with everything. The nice thing about this will be that you can take this circuit, connect it straight to a 12-volt lead-acid battery, and it will do its thing. You don't have to worry about it. It will just sit there and do what it's supposed to do. At least that's the goal. Anyway, so stay tuned for the next video. I hope to post up in a couple of days, and we'll actually start wiring this thing out on a breadboard and see if we can get it working with some real solar power. Although it is winter and I live in Michigan, so we might get maybe a watt. But no, it should be fine. We'll try it out. So until next time, see you later.